So hello again. Let's continue our discussion about MOS electrostatics. We've been illustrating the key concepts with something I've called an ideal MOS structure. Well, real structures aren't ideal. What I'd like to talk about in this lecture is a couple of the important non-idealities that we need to be aware of when we deal with real MOS structures. So this hypothetical structure that we've had, what was hypothetical about it is that we assumed that we had a metal and that the position of the Fermi level in this metal just happened to align with the Fermi level in the semiconductor. When that happens, when we apply no voltage to the gate, everything just lines up and the bands are flat. Well, what this really means is that the metal semiconductor work function difference is zero. So this is a very special case. We would say that in this special case, the flat band voltage is zero. When we apply zero voltage to the gate, there's no band bending. Everything is flat, no electric fields in the structure. Well, that doesn't really happen because if I take any metal, its Fermi level will be somewhere. The way that we measure the position of that Fermi level is with respect to a reference energy level. The reference that we usually take is the vacuum, so we would call that E0. And the distance between E0 and the Fermi level is the work function of the metal. So if I were to shine light on the metal and eject an electron from the Fermi level into the vacuum and detect that, maybe with a positively charged plate and measure the current, I would have to shine light with a frequency that gives me an energy of phi sub m, the work function. All right, there's a work function for the semiconductor as well. So I have the same reference, the vacuum level, and I have a conduction band. The distance between the bottom of the conduction band and the reference level, the vacuum level, is called the electron affinity, chi, and it has a known value in any semiconductor. There's a band gap of the semiconductor. If I add the band gap and the electron affinity, that takes me down to the valence band. But depending on how I'm doped, I have to subtract off the difference between the Fermi level and the top of the valence band in this p-type example. So the distance between the reference level and the Fermi level of the semiconductor is the semiconductor's work function. And that can easily change. You can see it would change quite a lot if this were an n-type semiconductor and the Fermi level would be up near the conduction band. So we have to account for the fact that the metal and the semiconductor are in general not going to have this ideal situation where everything just happens to line up. Depending on how I dope the semiconductor, I'll change its work function. Depending on what metal I use, I'll change its work function. And in general, we'll have a situation that would look like this. Here's a metal with a certain work function. The insulator I'm not really going to need to worry about very much because there aren't carriers in the insulator. I really don't even talk about a Fermi level in the insulator because if there just happened to be one electron in that insulator, it would swing the Fermi level up and down by a significant amount because its band gap is so large. So the Fermi level is sort of indeterminate in the insulator, and we don't even talk about it there. What we need to worry about is where the Fermi level is in the metal and where the Fermi level is in the semiconductor. Those two need to line up. So this is a more realistic example of what a metal oxide p-type semiconductor structure would look like before I put everything together. The Fermi levels do not line up, but we know in equilibrium, when we have one system, the Fermi level has to be constant everywhere. All right, so what needs to happen? Well, what needs to happen is that we remember that if we have an electrostatic potential that's positive, it pulls energy levels down. So there needs to develop, after there's a transfer of charge and electrons move from one side to the other side, there needs to develop a positive potential on the gate electrode to pull everything down so that its Fermi level aligns with the Fermi level in the semiconductor. That positive potential we would refer to as a built-in potential that will be there in equilibrium. It's needed in order to align the Fermi levels. That positive potential, Q times the built-in potential, is equal to the difference between the positions of those two Fermi levels. And the difference between those two Fermi levels is the work function of the metal minus the work function of the semiconductor. You can see in this example that's going to be a negative quantity, so I have a negative sign out here because we can tell that we need to have a positive voltage on this metal electrode in order to pull everything down and align the Fermi levels. So there will be this built-in potential, and this built-in potential depends on the metal semiconductor work function difference. All right, if we put everything together then, we're going to have a MOS energy band diagram that looks in the semiconductor as though we've applied a positive gate voltage. We have a positive surface potential. We've pulled the bands down and we're depleting the surface of the semiconductor. But we have now applied 0 volts to the gate. It is the built-in voltage that is already there in equilibrium that is responsible for this band bending. So this is going to be a very important factor that we have to account for whenever we make a real MOS structure. The potential in the semiconductor now is this built-in potential. It's there even when we apply 0 volts on the gate itself. So we have to differentiate between this applied potential and the built-in potential. We said that the built-in potential is equal to minus the difference of the metal semiconductor work functions. Okay, so in order to reach the flat band conditions, which was really the starting point of how we discussed MOS electrostatics in the previous lectures, we began with flat band and then we said, what happens if we bend the bands up with a negative voltage? What happens if we bend the bands down with a positive voltage? In order to reach that reference point, the flat band case, we actually have to apply a negative voltage to the gate electrode to pull everything up and make the bands flat. The amount that we have to do that is just equal to the metal semiconductor work function difference. The built-in potential was minus the metal semiconductor work function difference, so we have to apply the opposite voltage in order to reach flat band conditions. All right, so that is the flat band voltage. We can work out an example with some numbers so you can see how it all works out. This is the example that we have been using, P-type semiconductor doped at 10 to the 18th. We know how the hole concentration is related to the Fermi level, so we can deduce what the location of the Fermi level is with respect to the top of the valence band. We know what the effective density of states in. We put in the numbers, we do the calculation, and we can see that for 10 to the 18th p-type doping, the Fermi level is located just a little bit above the top of the valence band. All right, now let's look at what the metal semiconductor work function difference is. We're going to assume we have aluminum. It has a work function of about 4.08 electron volts. Now, the semiconductor's work function, we saw from the energy band diagram, is the sum of the electron affinity of the semiconductor, the band gap of the semiconductor, but that takes us too far. We have to account for the fact that the Fermi level is 0.08 eV above the bottom of the conduction band. So we make that correction as well. Well, the electron affinity of silicon is known. The band gap of silicon is known. We put in numbers and we find that the work function of the semiconductor is 5.09 electron volts. So it's larger than the work function of the metal. If we want to deduce the metal semiconductor work function difference, we just divide subtract the two. The work function is an energy. We're interested in the flat band voltage. To get a voltage, we divide energy by Q, and we find that the phi ms in volts, little phi ms, is minus 1.01 volts. That means in this particular MOS capacitor, about negative 1 volts on the gate would be the point at which the bands are flat. And that's sort of our reference point, and now we can bend the bands up or we can bend the bands down. Okay, so we have a flat band voltage of about minus 1 volt in this particular example. So we had talked earlier, we have been careful to label the gate voltage with a VG prime. The prime meant that we were thinking about a hypothetical metal that had the same work function as the semiconductor, which of course never occurs in practice. Now we simply have to correct that by adding the actual flat band voltage due to the metal semiconductor work function difference. So it's an easy correction to do. So in the end, we're simply left with this. The actual gate voltage is the flat band voltage, and then we have our volt drop across the oxide and our potential drop across the semiconductor, just as we had before. The flat band voltage is just the metal semiconductor work function difference expressed in volts. Okay, so that is one of the idealities that I wanted to talk about, and it has important consequences when we do measurements and try to understand them. You'll recall in the previous lecture we worked through an example with some typical numbers, and we computed the threshold voltage for this semiconductor doped p-type at 10 to the 18th. And what we found was a threshold voltage of about 1.3 volts. This was for the ideal structure, assuming no metal semiconductor work function difference. And I mentioned when I discussed that example that that threshold voltage is actually bigger than you would see in practice. You would expect a threshold voltage significantly smaller. Well, the reason that the threshold voltage is significantly smaller is that we have to add the flat band voltage. And the flat band voltage is about -1 volt. So we find a threshold voltage in this particular example that is about 0.3 volts. That's a more realistic threshold voltage for conditions like this. So the metal semiconductor work function difference is really a very important factor that we can't forget about and need to include in our calculations. Now, there is one more non-ideality that I want to mention. It's not so important in modern MOS structures. It was in the past. It is important when we use insulators that aren't silicon dioxide, and there's more and more of that going on these days. So it's worth talking about briefly. And that is the fact that when we have this amorphous insulator layer on top of a crystalline semiconductor layer, there are dangling bonds, and there's a thin, partially oxidized layer near the interface, and there's some complicated chemistry going on. And the result of that is that there is often a sheet of positive charge very close to that interface. We'll assume it's a delta function right at the interface. In a silicon dioxide system, it tends to be a positive charge. We're going to label that charge Q sub F. By F, I mean it's a fixed charge. Fixed means it doesn't change with bias. It's just a constant sheet charge that is there. N sub F is the density, the number of those charges per square centimeter. So this is a fact that is there. Now, there may be other charges. There are charges that are called fast charges. These are due more to the dangling bonds at the interface, and as we change the bias, then the charge changes. That distorts the CV characteristic and makes the analysis a little more complicated. It's not an important factor in modern silicon MOS structures, but in some of the exploratory devices and structures that people are looking at, it can be. There could also be charge in the oxide itself. In the early days of MOS, there was a lot of that. Over the years, a lot of work has been done to learn how to grow clean oxides with no charge in them. It's not a factor in today's devices, unless you're working on novel devices out of other material systems, and then you may encounter them. So to talk about charge in the oxide, I'm only going to talk about this sheet charge at the oxide silicon interface and ask, how does that affect the flat band voltage? So here's our situation. We have a sheet of positive charge right at the interface. Our gate voltage is still the sum of the volt drop across the oxide and the volt drop across the semiconductor. So if I take a fixed surface potential, psi sub s, that's the volt drop across the semiconductor. And then if I ask what gate voltage produced that in the presence of this surface charge, well, we need to compute the volt drop across the oxide, its electric field times thickness of oxide. We've seen earlier that the displacement field at that interface is equal to minus the total charge in the semiconductor. But now I've got to add the additional minus the fixed charge at the interface. I have to account for all of the charge. So when we do that, we will find that we get a different electric field in the oxide. Remember that the charge in the semiconductor is negative, so the second term here is a positive quantity. The fixed charge in a silicon dioxide system is always a positive number, so it's a negative number. So we're going to reduce the magnitude of the electric field in the oxide. We're going to reduce the the volt drop across the oxide. All right, if we do that, we find that the volt drop across the oxide, it was minus Q over C ox initially. Now the Q just has two terms, the fixed charge and the semiconductor charge. Oxide capacitance is the same. So our expression is the same. We simply have to add one more term due to the charge at the interface, just minus Q, fixed charge over oxide capacitance. So it's an easy change to make. So to summarize, the flat band voltage in the ideal structure, which we've been talking about in the previous lectures, occurs at 0 volts on the gate. The flat band voltage, no band bending in the semiconductor, no electric fields, that occurs at some finite voltage in any real structure, and there are two effects responsible for that. So one effect is due to the metal semiconductor work function difference. The second effect is due to a possible sheet charge at the oxide silicon interface. Okay, so we can go back to the example that we've looked at. We computed a threshold voltage of about 0.3 of a volt for this example when we accounted for the metal semiconductor work function difference. And we can do this again, assuming that we have 10 to the 11th charges per square centimeter. So just to calibrate you, this is not a large number. It's not a small number. If people are careful, they can produce 10 to the 10th charges per square centimeter. On bad systems, the charges can be 10 to the 12th per square centimeter. So we'll take something in the middle, 10 to the 11th. We multiply by Q to get the charge in coulombs per centimeter squared. We compute charge over oxide capacitance to find its contribution to the volt drop across the oxide. And what we find is that it's relatively small, very small, 0.01 volts. So we get a small correction to the threshold voltage. Now, this has happened over the years. This has happened in silicon MOS systems because the oxide has gotten thinner and thinner with each technology generation. That means the oxide capacitance has gotten larger and larger. Larger oxide capacitance reduces the volt drop across the oxide, and it has a smaller and smaller effect. The actual charge at the oxide silicon interface hasn't changed in many years, but its effect on the real structures has become quite small in modern structures. But again, if you're working on different systems, and there's more and more use of alternative gate dielectrics these days, this charge can become important, and it's something that we should be aware of. All right, so just to summarize this lecture, the flat band voltage in any real MOS capacitor occurs at a non-zero voltage that is easy to compute. The metal semiconductor work function difference minus the fixed charge over the oxide capacitance. And the gate voltage relation that we had before, which relates the surface potential to the gate voltage, is easy to adjust. We simply add the flat band voltage, which was 0 in an ideal structure, but is not 0 in any real structure. All right, so we're ready to move on to the next topic. And the topic I want to talk about next is a technique that is widely used to characterize MOS structures. We're not getting to transistors yet, but people will frequently build MOS capacitors and analyze their characteristics by measuring their capacitance versus DC bias on the capacitor. Turns out that one can extract a lot of information about the MOS system from those measurements. So it's worthwhile for us to see what that's all about and get acquainted with the capacitance versus voltage characteristics of these MOS capacitors that we've been discussing. That's our topic for the next lecture.